So is it visible full screen? Now is it visible full screen? Hello? It's full screen, na? Yeah. Actually, the total, I mean, TS session will be recorded and it will be updated. Okay. So, good evening to all of you. So, this is the second week of the course Characterization of Polymers, Elastomer and Composite, already taught by Professor Santanu Chattopadhyay from IIT Kharagpur. And from this side, I'm Samaresh Ghosh from IIT Roorkee. So, first of all, I hope that you have spent the first month of this new year well, and already this is the 1st February, so we have entered the second month of this 2025. So let's start. So before going to the testing of and characterization, so I will just briefly discuss what we have discussed last week, that is classification of polymers and their structure property relationship, how the structure can tune different physical and chemical properties. We have discussed crystallization temperature, we have discussed melting point, crystallinity, and also we have discussed copolymer, how they are different from homopolymer, etc. So today we will discuss about the different testing and characterization method. So these are the uh, sort of different uh, subject today we will discuss, that is structural chemical analysis, spectroscopic analysis, physical testing, dynamic testing, thermal analysis, morphological analysis, and environmental testing. Let's see. So first you should know that there is two term, characterization and testing, but they are not the same. It is different. Testing and characterization is different in the way that one is the broad range, another is the a sub part of the previous one. That is, testing is the sub part. So what characterization refers? One minute, someone is waiting. So what characterization is referred? Characterization is a range of process to probe material structure and their properties. And what is the importance of characterization? Without doing the characterization, we cannot understand that why some material is showing this property, why that kind of structure showing this type of property. And also we cannot scientifically predict that if I am synthesizing or if I am processing some material, how it will behave when it is finally applied in real-time application. So that's why we need to do characterization very deeply to understand the science behind the material's behavior. And then it comes the testing. Testing refers to the evaluation of performance of material under different condition, under different environment, and also when ultimately the product is performing in the real field. So broadly we can say that material characterization involves a large number of analytical techniques to evaluate its chemical or physical behavior, and it is different from material testing in that it is related to its fundamental science or fundamental structure rather than the applied environment or applied condition. But testing, that is mainly depends on that what is the condition when I am performing a specific testing. In that way, testing is different from characterization. Okay. Now, what is the importance? So I have already discussed that why I should do characterization, why I should do the test. Now, uh, otherwise I cannot probe without characterization, doing characterization I cannot probe the material chemical or physical behavior. So there are different characterization method. Chemical characterization, like we will discuss one by one. There are spectroscopic characterization, thermal characterization to probe the thermal property or thermal behavior, structural characterization, and physical testing, dynamic testing. So in the chemical analysis, there are also different characterization, like elemental analysis. To do to know the elemental composition, we have to perform different characterization technique. We'll discuss those later. Another one is the solvent extraction. So if you dipped a material in a specific solvent, so after some time or after few days, some additives or plasticizer or different chemicals can diffuse from your material to the solvent. In that way, you can say what are the different material is present in your material. And obviously, those materials should be physically bonded with your matrix. Another one is the ignition test. If you ignite, you may see some flame, you may see some uh, volatile gases are coming. From that, you can see, you can predict what are the chemical element present there. Like I don't know whether some of you have performed, that is, it is showing here platinum wire. This is platinum wire. You dipped, put some material on the platinum wire. This is called the flame test, and you put the platinum wire in a flame. When you put the platinum wire in a flame, if the material has some different element, they will show specific color. For example, if sodium is present in your material, it may show golden yellow type flame. From there, you can say, okay, there may be presence of sodium. And also for strontium, it usually show a crimson red type color. So from this analysis, you can just predict that okay, these are the elements may present. For confirmatory test, there are different analysis. Okay, now come to the spectroscopic analysis. So what does the spectroscopy mean? Spectroscopy basically the study of light and matter interaction. If you put light, the matter will interact with the light and it will show some changes what happened if it is under that light. Now we know there are different wavelength of different light from 10 to the power minus 13 nanometer to 10 to the power 6 nanometer. And also we know higher the wavelength, the lowest is the energy of the light. This is the visible region, that is 400 nanometer to 750 nanometer. So based on this different light, we can do different spectroscopic analysis. Like microwave, where microwave is used, and what is the material behavior if it is irradiated with the microwave light. UV vis, that is you put your sample and you may solubilize it in a specific solvent. You put the that cell inside the instrument, you will get some peak. From there, you can characterize that what are the different transitions are happening in your material. Infrared, this is also one kind of structural analysis to probe a different what are the different functional group those present in your material. For example, if you are if you have like NBR type rubbery material, acrylonitrile butadiene rubber. So the presence of C triple bond N group, that is nitrile group, if it is there, from infrared, you will get a peak around 2000 to 2200 centimeter inverse. From there, you can say, okay, there may be presence of the nitrile group. If it is some polyester, you will get a characteristic peak around 1700 centimeter inverse. That is corresponding to your carbonyl group. So from infrared, you can say what are the different functional group present in your material, and from that you can say that okay, this material is this kind of the material maybe it is polyester, whether it is unsaturated polyester, you will get different result from the infrared spectroscopy. The next one, the X-ray. X-ray is the XPS, X-ray photoelectron spectroscopy. From there you can exactly calculate how much different element present in your material. And the last one is the nuclear magnetic resonance spectroscopy, that is NMR spectroscopy. There are different NMR technique like 13 NMR, proton NMR. So for polymer, it is difficult to perform because it's not difficult. The main problem is usually for polymeric material, you will get a broad peak in proton NMR technique. But if it is a small molecule, you will get sharp peak at different delta value. So these are the different spectroscopic technique to probe a material structure, and from that you can predict some different properties. Next is physical testing. So physical testing, we have last week we have touched this in a very short time. So to perform this, you need to do different physical testing. So in physical testing, there are also different testing methods. So briefly, it evaluates the physical and mechanical properties and also its appearance and density, its interaction with different solvent, organic solvent or water, and also other different physical technique like melt flow index, your scratch resistance, its physical appearance, whether it is colored, whether it is black or some color pigment is there, its density, and very important, the mechanical behavior and also the viscosity of your material. And for polymer, the viscosity is directly related to the flow behavior of your material. So that's why rubber is a viscoelastic material. It has viscous part, also it has elastic part. So you need to know the what is the viscosity of your material. From there you can predict that when it will be used or when it will be processed, then how much energy it will consume. Because you may know that if a material is too much viscous or it is too much elastic, the material behavior during the processing will be different, and accordingly you have to set different parameters, different processing parameter. For example, like if you know that processing of conveyor belt or processing of tire material, if the viscosity is too much high, and you will get the Muni value higher, the viscosity, the Muni value will be higher, it will be very difficult to process through the calendar. So you have to optimize the viscosity to get the smooth processing. If you have question, you may stop me anytime, and we will discuss. So till now, if you have any doubts, you can ask me. The next one is the melt flow index. So what is melt flow index? You should put certain material inside the instrument, you will press it, you will heat it, and the whatever the amount of material is coming from the instrument by unit time, that will be your MFI value. Then higher the MFI value, the lower is the viscosity. You will get higher amount of material per unit time. Now, most important thing is the dynamic testing. So till now we have discussed this physical testing, and also dynamic testing is coming under the physical testing, but the testing method or testing condition is different. So dynamic characterization relates to the molecular structure and of polymeric materials, to the manufacturing process, and to the field of performance of engineering product. So obviously any material those are used in uh, real field, those are not static condition. For example, let's say tire. When a car is moving, the tire is in the dynamic condition. So it is stressed and then it is released. When some part is touched with your road, that part is under the stressed condition, and again after few seconds it is the stress is released. So it is in uh, dynamic condition. So after a certain frequency you are giving stress and again you are releasing it. So dynamic properties play an important part in comparing mechanical property of different polymers for quality, performance prediction, failure analysis, and new material qualification. Dynamic properties have utmost importance when polymeric materials and components show heat generation and fatigue related heat. And also when you are doing the dynamic test, you may have experienced that under the when a car is running, the tire is already in a very hot condition. So temperature generation is there, heat generation is there. So there are different testing methods. You may sweep the strain, the stress relaxation, fatigue, frequency sweep, temperature sweep, and creep. We'll discuss what is creep, what is stress relaxation, what is frequency sweep in the next slide. Before that, let's discuss about other physical properties. So this is thermogravimetry analysis, that is TGA. Last week we have also little bit discussed. So what we study here, you are scanning temperature and you are measuring the weight loss. If anybody have experienced TGA, please you may ask question. So what we plot in thermogram, we plot weight loss versus temperature. For that, you need to take a very small amount of your material. You put the material inside a TGA machine, and there is also a standard material. With respect to that, you are measuring the weight loss. For example, a rubbery material, there are different component because it is a composite. There are filler, there are plasticizer, there are base rubber material, there are different additives, etc. So with uh, temperature, when you are increasing the temperature, first maybe plasticizer or additives will be vaporized, then your rubber, and finally the filler material. So from the thermogram, you will see different step of weight reduction. From that, you may predict what are the different elements present on the composite material. And also, to prove the thermal stability of your material, you will get knowledge from the TGA analysis. So we are scanning temperature and we are measuring the loss of mass with temperature. So for usually for inorganic type material, you will get always a few weight percentage remained even after 800 degrees centigrade. That is because of inorganic material will ultimately convert in the oxide type of product. For example, if zinc oxide there, it will remain as a zinc oxide till 800 or above 800 degrees centigrade. But if there are organic material, for example, any rubbery material, so after 400 degree or 500 degree centigrade, all organic part will be converted to your CO2 and it will be released. Anybody have doubt, please ask. First of all, in TGA, I will repeat, we are scanning the temperature, we are measuring the mass loss. Depending on your material, the mass loss step will be different, and the composition, depending on your composition of your material, there will be a different step of mass loss. If anybody have question, please ask, because TGA is very important in polymer field. And also you may perform TGA under inert atmosphere. For that, you need to provide nitrogen instead of oxygen. In that case, you may get different result. So if somebody doing the same TGA analysis of the same material in different condition, the two result will be different. If it is under the inert atmosphere, the result will be different. If it is in open atmosphere or in presence of oxygen, the result will be different. Okay. Yes, yes, that is very good. That is very good question. Thank you. So we are scanning the temperature. Now, what is the rate of increment of your temperature has a very important role in the to determine the result. For example, usually we do TG analysis at 10 degree per centigrade per minute increment. So the temperature you set from room temperature to 800 degree centigrade, and now you are increasing the temperature at a rate of 10 degree centigrade per minute. Now if someone is doing the same test with the same temperature range, but he is performing that experiment under the 5 degree centigrade increment per minute, the difference will be, there will be a slight change in the different weight loss. If someone is performing at a higher rate, the degradation temperature will be slightly shifted to the higher temperature side. Understand? For example, if any additives are vaporizing, let's say 150 degree centigrade at 5 degree centigrade, if I am increasing the temperature at a rate of 5 degree centigrade per minute, now the same material, if I do the same experiment at 10 degree centigrade per minute, instead of 150 you may get 160. That will be the difference. So it will be right shifted. Now why this is happening? Because if I am increasing the rate at a higher level, so maybe because we are probing temperature by a thermocouple. Now the sensitivity of your thermocouple is also very important. It may be possible that that much of temperature is not reached up to the material, but I am saying that we are increasing the rate at a very, if it is very fast, that maybe it will feel that temperature when it is already right shifted. That's why we will get a 160 or 165, but it will not be very absurd. Usually you need to perform at a lower temperature rate to probe deeply. Sometimes if there is a very small composition, it may be, you may skip it if it is very high rate. If the rate of increment of temperature is very high, it may be skipped in your thermogram. So it's better to do the test at a 10 degree centigrade or 5 degree centigrade per minute. Now it is clear. Now what is the importance of the rate of increment of your temperature in TG analysis? Okay. Next is the laser flash analysis. It is thermal diffusivity. Dynamic mechanical analysis. This is very much important. We will discuss it later. Another is the differential scanning calorimetry, that is delta H. So DSC is, so in TJ we are scanning the temperature. Now in case of DSC, we do the we will increase the temperature, but we will measure what is the change in the enthalpy, delta H value. So delta H versus temperature will be the ultimate DSC data. If you say DSC data, it is plotted in y-axis, it is delta H, and in x-axis it is temperature. Usually we determine TG from DSC of any polymeric material. You can also determine the TG from DMA analysis, and you may get different result from DMA. Thus for the same material you may get TG at different temperature from DMA or from DSC. That is basically because of the technique what you have applied to determine the TG. Now in DSC, usually you need to do the DSC for rubbery material from minus 30 degree centigrade or minus 25 degree centigrade up to 300 or 400 or maybe 800 degree centigrade. Now in DSC what we do, there are two base. In one base it is your material of interest, and another one it is containing the standard material. So with respect to standard material, you are measuring the temperature difference. Based on that, you have to provide heat to maintain the same temperature difference. In that way you are measuring the change in the change in heat with respect to temperature. So from DSC you will get PG, you will get melting point, you will get cross-linking temperature, you will get crystalline temperature. And also, if the direction of delta H, that is change in heat, it's maybe negative towards upper side, or if it is negative towards downside, so the peak will be vice versa, it will reverse. Okay, for crystalline material you will get sharp peak because of melting of crystalline zone. For the amorphous material you will get a sharp peak, and that will correspond to your Pg. And also for DSC, the rate of increment of temperature is very much important. If you perform the same analysis at a higher rate, you will get Pg at higher temperature, and also your melting temperature will be in the right hand side, it will be shifted in the right hand side if it if you perform the analysis at a higher rate, 10 degree or 20 degree centigrade per minute. The next is dilatometry, that is you will measure the change of volume. Evolved gas analysis, that is you will check what the gas is released if a material is burned. So these are different physical characterization method to prove the physical properties of your polymeric material. Now in thermal analysis there are different techniques, that is dielectric thermal analysis. Here dielectric permittivity or loss factor is measured. Differential thermal analysis, that is temperature difference, you measure temperature difference with respect to standard and your material of interest. DSC, that is heat difference with respect to standard, what I have discussed already. Dilatometry, that is the change in volume with respect to temperature. Dynamic mechanical analysis, that is mechanical stiffness, you check mechanical stiffness and dampening with respect to temperature. Evolved analysis, gaseous decomposition product, those gases are evolved. To check those gases, you may check it from GC. TG analysis, that is you are measuring the change in mass with respect to temperature. And thermomechanical analysis, so you are scanning the temperature and you are measuring the change of the dimension of the material. And in case of thermo-optical analysis, you are checking the optical properties or optical uh, changes what happened with respect to the temperature. The next important analysis is the morphological analysis. So from morphology you may get various information about the material physical behavior, the roughness, the distribution, the dispersions of your filler in a polymer matrix. Bulk morphological analysis is used to observe tiny details in samples as small as individual atoms and provides high level of detail about material complex nanostructure. So there are also different characterization technique for to study the morphology of your material. So first one is the optical microscopy. So you put the very small amount sample inside a optical microscope and you will check whatever the bulk morphology of the material. But to probe more deep or in the nanometer level, you have to go to electron microscopy, because through light we cannot go above 10 to the power minus 4 meter. So first one is the scanning electron microscopy, that is SEM. The second one is transmission electron microscopy, that is TEM. There is scanning tunneling microscopy, that is STEM. Atomic force microscopy, that is AFM. Chemical force microscopy and laser microscopy. So here I will discuss little bit about SEM and AFM. So scanning electron microscope, you have to put a very small amount of sample, either by dispersing or as in solid condition inside the probe, inside a base, and you have to coat through gold. So first you have to put inside a sputtering machine First you have to coat your material with a gold nanoparticle, then you put that coated material under the instrument and you will see the morphology. So from SEM you may see, I don't know whether you have see the SEM image or not. You can go up to 200 300 nanometer. In that range, what from there uh, you can clearly see what is the distribution of different filler material or dispersion of filler material or other additives in your uh, polymer matrix. From that, if there is aggregation, it will be visible from your SEM image, and then you have to again reprocess it, because if dispersion or distribution is not homogeneous, obviously the material property will not be homogeneous, so that will create problem. So to know that, you have to do the SEM analysis. From there you can directly see whether the dispersion is efficient or not. So this is scanning electron microscope. So electron gun is there. We'll discuss maybe in 7th or 8th week very deeply the SEM and TEM, etc. As first, for your own interest, I am just deeply touched at what we do with SEM and TM. These are very costly machine basically. An atomic force microscope, here you are probing the different atomic level force when your material, and there is a lever that will touch. There is a very small atomic size beam that will touch on your surface of your material, and based on different interaction it will feel different atomic force. Based on that, it will form an image. From there you will get the morphology. Now in physical testing there are different uh, parameters you need to measure. So very important, this is tensile strength, shear strength, elongation at break, compression, shear, impact strength, flexural strength, abrasion resistance, hardness, set property, resilience, ductility, also stiffness, toughness, hardness, color, melt flow index, water absorption, viscosity, and electrical conductivity. So these all are under the physical testing, and these are very important for engineering type of material. You you need very high tensile strength or shear strength to for high end application. Now here the preparation of sample is very important, and for that you need to go through different ASTM or different international standard like ISO, ASTM or DIN standard, and also Indian standard, and sometimes different company have their own standard. Based on that you need to prepare different testing sample. So this is torque versus time plot, and from there you need to calculate what is the curing time, how the material is behaving when the cross linking is happening, and based on the result you can predict that how much tensile strength you will get when the material will be finally it will be produced. So for compression the force will be in that direction. For tension it will stretch in different direction of the same material. For bending there is direction of force will be different. Shear, where you are uh, uh, two surface at different angle, it is stretched. For torsion the angle of giving stress is different, and this is very important curve for uh, rubbery type material, because the curing or the curing time, that is TC90, and also from when the curing start, that is TS2 value, that is also very important. Based on that you can set the different temperature during calendaring or during building, and also uh, when it will be ultimately cross linked under press, what will be the temperature or what will be the rate of increment of your temperature. This is a simple stress strain curve for brittle type of material or ductile type of material. For brittle one, we know the modulus is very high, but the elongation of break is very low. So it will, after certain strain, it will be broken apart. And also from the nature of the cracked surface, you can predict what is the nature of failure. For brittle type of failure, it will it will be like this. There will be no stress concentration point. The surface will be very smooth. So from there you may predict what is the problem in your material, or what will be the change in the formulation. For the ductile type of layer, it will not be very smooth surface. So you are stretching, so stress concentration will generate, and finally after certain time it will break. The next physical testing is the hardness. Hardness is obviously very much important. And what does it mean? It is basically the resistance towards permanent deformation. Resistance of a, in a general way, it is resistance towards permanent deformation. But we can also say that hardness is the resistance of a material to indentation or abrasion or scratching or cutting or shaping. Now, hardness testing is a non-destructive method. After performing the test, you can use that material. Application of constant load via rounded or pointed object. Based on that, there are different uh, term of the hardness tester. So in next slide I will discuss that. Now what are the different factors affecting the hardness? So first of all, the load on the indenter. If the load is very much high, you will get the hardness is low. But if the load is small, you will feel like if you press some material, if you pressed in a very rigidly, it will be damped. But if you put very small amount of stress, it may not be deformed. And also the nature of the load, whether it is impact type, whether it is stepwise increment of stress, or whether it is continuous loading, and also the duration of load. And the another very important parameter is the indenter geometry, because based on that, the force filled by the material will be different if the geometry is different. So first one is the Brinell, where the indenter size, indenter uh, dimension is circular type. The Vickers, the angle is 136, and it is tetrahedral type of indenter geometry. And in case of Rockwell, the angle is 120 degree. So basically these all are used for the hard type of material or plastic type of material. But in case of the rubbery material, we used to do the durometer test or shore hardness test. So we know that shore A and shore B. So for hardness rubbery material, we use this type of hardness tester. There is a very small pin type of material, that is indenter. You pressed it and you will get different hardness from the uh, digitally showing uh, uh, this mark, whether it is 60, so a 60 or 70 or 80, depending on different composition. Now from the hardness, you can predict what will be the tensile strength. Now if you have experience, otherwise you cannot predict. If anybody has experience that, okay, for NR, if I am getting hardness around 60 to 63, I will get tensile strength around 160 or 170 megapascal. And hardness is very much important because it will affect the abrasion property also. It will affect your dynamical property also. So you need to perform hardness test for any rubbery type of material at a very preliminary level, but it is very important. The next is abrasion. So abrasion basically the loss of material, but the term wear and abrasion sometimes confused, but wear is more general term. It is covering loss of material by any means. But in case of abrasion, there is uh, friction in two different surface. It is not the same surface. So here this is Dean aberration tester. This is the cloth. It has also own standard. What is the length? What will be the width? And the dimension? The rubbery material is put here. From here you will see it clearly. A circular type rubbery material you should put here, that is sample holder, and you will rotate these circular type uh, uh, rotor at a specific speed, and then you have to calculate what is the loss of material after one cycle. So first you need to check that is the aberration index. So you need to check a standard material. Based on that, you need to check the loss of volume, it is volume of your material of interest, and the ratio into 100 is the aberration index. Now I will ask one question, that aberration resistance is important where the material is carrying or it is in a dynamic condition. In that case, aberration is very much important. So I will ask you, if a material has a hardness of 70, so a 70, and by changing the composition, if the same material is showing the hardness of 60, what will be the impact on your aberration resistance? Have you got my question? That if a material has a hardness 70 SORE and another one is having hardness 60 SORE, aberration resistance will be better for which one? Anybody else? Yeah, you are right that hardness which one has a 70, the aberration resistance will be better. Now why it is so? Because we know that hardness is the resistance towards permanent deformation. Now when you are abrading, the material surface is continuously going under friction with the this specific type of cloth. This is the very rough type of cloth material. Now if the chemical bonding is very much high with your matrix, and also if the polymer chain are very highly bonded with another polymer chain, and if the filler content is high, and if the dispersion is very good, so the matrix filler interaction is very good, and your because of higher filler composition, the hardness will be higher. And that's why when you are doing the friction, it will not be irradiated from the material surface. So usually for higher the hardness, the abrasion resistance will be higher. If the hardness is low, for example, if you use those in case of conveyor belt, though material those are used with the fabric, usually those type of material have hardness around 50 to 60, but the top layer material or bottom layer material, usually it need hardness around 65 70, and obviously it should have better abrasion resistance. Now next one is DMA analysis. DMA is the most important characterization or testing method to investigate the properties of material under dynamic condition, and from the result you will get to know what will be the performance during the real time application, or its in the field for performance in the field. To study the deformation behavior of a material over a range of stress, strain, time and temperature. Very useful for measuring viscoelastic property, determines the modulus of the material, complex modulus. Now complex modulus term is very important. So what is complex modulus? Because we know that rubber or polymer material, usually we used to say these are viscoelastic material. Now, if a material is purely elastic, that is 100% elastic, in that case the loss or flow behavior is totally, it's not there. If any material is purely viscous, that will have very small amount of y value, modulus value, it will be flow. Even there a very small stress, it will be flow. Now complex modulus terms is appeared because in case of viscoelastic modulus there is always storage modulus, that is related to your elastic component of your material, and the loss modulus, that is related to the viscous property of your material. Now if any material has higher viscous property, we used to say it is a viscoelastic, or if it has a higher amount of elastic component, we may say as a elastoviscous. Next is the tan delta, we will discuss it later. That is basically loss modulus by storage modulus. It mainly measure either strain or deformation against applied stress or vice versa. So you may put the strain and measure the stress, either you put stress and measure the strain. So there are different mode: strain sweep, frequency sweep, temperature sweep. Now time temperature, why it is important? Now in case of polymer physics, the time temperature superposition is very important. For the same material, if you are performing this DMA test at a specific time, at a particular time, and the temperature is fixed, but sometimes you need to wait for a long time, but in that case if you increase the temperature, you can do that same test at a very small time, you will get the same result. Mode of deformation, that is tension, bending, compression or shears. Sometimes you are putting the stress at a specific interval, in that case of oscillation or rotation. Now this is showing what is the 100% elastic. That means you are giving stress and you are getting the strain at a without any phase lag. So at maximum stress you are also getting the maximum strain. That means the input and output, those are following the same phase. It is not in, there is no lagging. That's why it is sinusoidal curve. So both stress and strain without any delta, any phase gap. That's why the delta is 0. In case of viscous, that is if it is 100% viscous, so there is a phase lag of 90 degree, that is delta equal to 90. That means the minimum stress, your maximum, when the stress is minimum, in that case I mean the response is delayed by 90 degree. But in case of viscoelastic, you see there is a angle in between 0 to 90. So if the lag or delay is in between 0 to 90, we used to say the material is viscoelastic type. If there is no lagging, the material is elastic. If there is a phase lag of 90 degree, that material is purely viscous type of material. If you have any question, you should ask me, because this is very important. It is clear to all what is viscous, what is elastic and viscoelastic, based on this stress strain curve, sinusoidal curve. Then I will go to the next slide. And here for your information, I should add another point. For example, if you are using, say, natural rubber without using any filler, in that case the viscous part will be higher. But when you are incorporating filler continuously, then elastic part will increase with time, with the addition of the filler amount, and based on that you will get different result. because now elastic component is increasing with the addition of the filler. Okay, so from the viscous you are moving towards the viscoelastic to elastic. If there is a very high amount of filler, you will see there is a the elongation of break will not be very high, because there is a fracture will happen, and also in between filler what is called as a pain effect. Because of that, ultimately your material will break down. Okay, now what are the different terminology? The stress, that is force per unit area, that is Newton per meter square. The strain, that is deformation per unit length. The modulus, that is stress by strain, usually the unit is Pascal or megapascal. Now what is compliance? It is basically uh, strain by stress, that is reverse of the Young's modulus. And viscosity, what is viscosity? That is stress by strain rate. Now in case of complex, that is in case of viscoelastic or viscous type of material, the term complex stress or complex modulus is come. Now what is complex? It is same, but we used to denote by putting a star. It is complex stress by strain. Now what is the storage modulus? It is complex stress by strain into cos delta. It may be also, you may put in a sin delta, because there will be change only in 90 degree, otherwise it is same. Now loss modulus we used to denote by E double prime, that is stress by strain into sin delta, and loss factor, that is tan delta equal to loss by storage. Based on the tan delta value, you may say what is the whether viscous part is higher or whether elastic component is higher in the matrix in your material. Now what is stress relaxation? Hmm. Yes, please. Okay, 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 okay. So modulus is stress by strain. Now if you put stress, for example say 5 Pascal, you are putting 5 Pascal of stress. If there is no loss, loss means how the loss happen? The loss, because of maybe heat generation, it may use the energy, and it will dissipate the energy through heat or through flow. I mean, it's not absorb total energy. What is force? Force is obviously one kind of energy. Now when you are putting or giving energy to a material, if it is absorbed totally, the strain will be different. But if there is a, for example, if it is let's assume two marble, if you if it is elastic collision, or I should give you better example. For example, you should let's say a tennis ball, you put at a certain height, for say it's from 5 meter, you are it is falling at a length of 5 meter. So after collision with the ground, whether is it coming up to the same height or it is little bit low, that is the loss. That is because of the viscous part of your material. So if you put the ball from a height of 5 meter, and after colliding with the ground, if it is coming up to 3 meter, that 2 meter, that is equivalent to mgh, that is mass and gravimetric constant, that is gravitation constant, and height, that is the energy. So if it is elastic, it should convert total. But if it is not elastic, if there is a loss, so it will not convert the total energy. There is loss little some amount through by some means heat or something else. That's why you should not see that after hitting the ground, it will not come up to the same height because of the loss. Understand or not? yeah, store the energy, and when it will release, it should release the same amount, but it's not same amount because their loss is happened. And now, yes, now why this loss happened? Because of the viscous component. Because of the viscous component. Because viscous component cannot release the same amount of energy. You may compare it with is your elastic collision. For example, if you collide two marble, it's more idealistic. Though it is not purely ideal elastic, but still you can say almost 99% elastic collision. That's why after collision, it will again uh, go apart from each other. It is that it is the tan delta or loss factor, and from measuring that tan delta, you will get the idea of your glass transition, where it will cross the if you plot the storage modulus and loss modulus versus strain, where it is crossing the each other, that particular point will be the TG value in the DMA analysis. So next is the stress relaxation. So it is also a time dependent property. What is stress relaxation? You put a constant strain, and you will see that after certain time the stress is reducing. That is the stress relaxation, and that's happened because of the viscous behavior of the material, because the material will flow, it will not uh, uh, fixed at a same strain after certain time. So that's why, for example, if you see the any rubber band, if you put at a specific strain, say 10% elongation, and you put at a constant elongation, you will see after certain time it will be lumpy because the stress is reduced. That is because of the viscous component of your material. Now the next is the creep. It is the constant force is applied to the rubber, and the change in deformation with time is monitored. So this is stress relaxation. So you put a specific strain, you reached a stress value up to sigma, you fix the strain at that same level, and you will see there will be a decaying of your stress. That is because of the viscous behavior of your material, because material will flow. The next is creep, that is the fixed stress, and you will notice the deformation behavior with time. How with time the deformation behavior is changing. So you see the deformation is increasing, and then it is becoming the constant. Now there is a creep failure or different failure mechanism also there. So one of the reason why it is important, because from that you will predict that when the material will be used, where deformation is very important, where the material should retain its dimension, in that case the creep will important to predict the dimensional stability also. Now what is fatigue? Fatigue is a process of progressive localized plastic deformation occurring in a material subjected to a cyclic stress and strain at a high stress concentration location, that may culminate in cracks or complete fracture after a sufficient number of fluctuations. For example, uh, if you let's say tire, it's going through a localized plastic deformation, it's going through a cyclic stress, and then again it is releasing releasing stress. So it is a cyclic process of stress and strain. In that case, the material will undergo a fatigue type of uh, behavior, and that will create some stress concentration after certain or after a number of cycle of stress strain, and ultimately that will generate a crack, and that crack will propagate with time, and ultimately your material will be uh, fractured. Now fatigue failure is the formation and propagation of cracks due to the repetitive cyclic load. So to investigate or to predict what is the stability may material under repetitive cyclic load, you need to go to the you will go through the fatigue failure study. So we have discussed the different physical testing. Now the another important testing is environmental testing, because ultimately your material will be will come in the open atmosphere, and it will feel different environmental um, component, like your fog, your different chemical environment, different heat, or humidity, or UV. Based on that, you need to perform some environmental testing. So on the materials perspective, there is maybe cyclic corrosion, there may be chemical or fungus type of resistance, there may be sand resistance or dust resistance. These are usually important for coating type of material, how much sand resistance it have, or how much dust resistance it have. There is also fire and flammability. You need to check what is the uh, fire resistance, the capability of the material to resist fire or fire propagation. On the climate perspective, there is a temperature, humidity, altitude, icing, thermal vacuum, UV weathering, and hydrostatic and pressure cycling. So, for example, if your material, those rubber is say conveyor belt, those are used in underground in mining environment. In that case, you obviously or certainly you need to perform that fire resistance property. Otherwise, it will be not applied in that type of environment. There is also salt spray test, usually for coating type of material. For example, uh, those coating are used in submarine or NAC. So those are in the NaCl. In sea water, we know there is a concentration of NaCl is very much high. So you need to perform the salt spray and test analysis. For that, the standard, there are different standard. You need to prepare 5% NaCl solution. You dip the coated metal or coated sheet inside that solution at a specific temperature, and after certain time, you need to check whether corrosion is happening or not, whether there is a surface rupture happening or not. Humidity resistance, it is important for coating type of material. For that, you need to coat this dimension 150 by 150 and with this 4 steel panel, and check under a room a little bit higher temperature 40 degrees centigrade with tap water how much humidity or it can resist, because at different environment the humidity percentage will be different, and also based on temperature the humidity uh, will be different in different location. QUV test, this is basically the UV resistance technique. For that, there are different UV wavelength. UVA, in that case, you need to provide 315 to 400 nanometer UV, that is lowest energy, and also another one is UVB, that is 280 to 315, and another is UVC, that is 100 to 280 nanometer. Now we know that if the wavelength is higher, the energy is low. So lower the wavelength, it will affect most your material. So for the coating material, as it for example exterior type of material, exterior coating, or if in case of rubber, that may, we know that if it is natural based rubber, so there is unsaturation in your backbone, and there is chance of formation of radical in under the presence of UV light. So in that case, you need to do the UV resistance testing. The chemical and solvent resistance, because sometimes the material may carry some chemicals, those are very corrosive. In that case, you need to do this type of test. Microbe resistance, that is standard practice for determining resistance of synthetic polymeric material to different fungi. and fire same resistance. For that case, limiting oxygen index, you should know what is the uh, Ly value. Based on that, you need to do the uh, different testing, and higher the Ly value, that means it is less prone to uh, fire, and lower the Ly value, it is much more prone to fire. So if any material those will be used under mine, it should have higher Ly, so that the chance of uh, uh, fire problem will be low. So here I have provided few question. Yes, yes. Ly is the limiting oxygen index. That is the minimum amount of oxygen you need to start the fire. So first one is, which one of the following is considered as environmental testing? Is anybody? I have already discussed the DSC, differential scanning calorimetry. Answer is B, salt space test. Now salt space test, actually this is important for the coating type of material, because uh, those the sieve and submarine which are usually used under the sea water, or under the inside the sea water level, in that case you need to do this test, so that the coating will protect your metal body from the corrosion. Now I don't know whether you have heard those terms, the viscosity. There are different viscosity term that IUPAC provide. It is inherent viscosity, specific viscosity, intrinsic viscosity, reduced viscosity. These are for the polymeric type of material or for any solvent. Now anybody please, uh, what will be the answer? I mean, the left column and right column, what is the inherent viscosity, and it's corresponding to which one is the inherent viscosity and specific viscosity, and the rest all. Anybody response please? Do you know what is inherent viscosity? And this is the specific term to determine the viscosity, or to uh, categorize different viscosity. These are the mathematical term. Okay. So what is inherent viscosity? Inherent viscosity is eta Sp by C at C tends to 0. That is the inherent viscosity. What is specific viscosity? Specific viscosity is eta minus eta 0 by eta 0. What is intrinsic viscosity? Intrinsic viscosity is ln eta relative divided by concentration, and reduced viscosity is eta relative minus 1 divided by concentration. Understand? These are just to denote different viscosity. So IUPAC, uh, these 4 different viscosity parameters they have uh, identified, and this is mathematically expressed by this equation. Eta is the viscosity. It's not a dynamic. Eta is not dynamic. Eta and eta 0, that is, it is the your material at a different concentration, and eta 0 means it is at a very dilute condition. So from here you are getting different. You see that if the specific viscosity, relative viscosity is actually eta by eta 0. From there you will get specific viscosity, that is eta minus eta 0 by eta 0. From there you are uh, what I can say, from the one you will get that different value. So just to denote different viscosity, it's not absolutely different from one another. From one, it is just dividing by concentration, dividing by uh, viscosity at zero concentration, they are getting different viscosity value. Yes, actually, you know that Markov equation, you have heard Markov equation. Okay, so in Markov equation, that is used uh, intrinsic viscosity. From there you will get the weight average molecular weight. So IUPAC identified these four different terms for different purpose. Now the basic is relative viscosity. It is not mentioned here. Relative viscosity means viscosity at different concentration of a same material or for a same solution divided by viscosity when the solution at a zero concentration of solvent. From there, if you get the relative viscosity, then again you are getting the eta minus eta 0 by eta 0, because eta 0 is known. It is the viscosity of your solution at a zero concentration or very dilute concentration. And again, if you are getting these uh, intrinsic viscosity, you will get reduced viscosity, that is eta relative minus 1 divided by concentration. And just these are the mathematical analysis and different calculation only for different purpose. The basic is the reduced viscosity, that is eta by eta 0. What is eta? Eta is the viscosity of your solvent of your solution, and eta 0 is the viscosity of the solution when the concentration of solute is very low. That is the relative viscosity. From the relative viscosity, now you are deriving different viscosity term. Sometimes you are dividing the by concentration of the ln value of the relative. Sometimes you are dividing by concentration at concentration close to 0. Sometimes you are dividing after deducting the minus 1 by concentration. It is the same. I mean, from relative you are getting everything, just this is a mathematical uh, derivation. So first you need to know the relative. From relative you will get the inherent, you will get the specific and reduced. That's all. If you have doubt, please ask. Whether it is clear or not. It is just mathematical derivation. So first you need to know what is the relative viscosity. This is the eta relative. Now you see eta relative equal to eta by eta 0. Okay. Now what is eta? Eta is the viscosity of a solution at a particular concentration. Now eta 0 is the viscosity of the solution when the concentration of the solute is very low, at a very infinite dilution, you may say. So if you know the eta relative, now see you are just doing different mathematical derivation. Eta relative minus 1 divided by concentration is your uh, specific viscosity. If it is ln eta relative by C, it is intrinsic viscosity. If it is eta specific by C at C equal to 0, it is inherent viscosity. That's all. So once you know the eta by eta 0, you will get the all the different viscosity value. Now for different equation, like for Markov equation, you need to know the intrinsic viscosity. That's why they are they have derived these four different viscosity. Okay. Now what is compliance? We have already talked about compliance. We have talked about Young's modulus. So what is compliance? Yeah, that is strain upon stress. Now this is the reverse of your Young's modulus. So till now, if you have any doubt what we have discussed today, you should ask me. We have this. Okay, okay, you should ask. Hmm. Okay, okay. Actually, what is the time of that class? Okay. That is already fixed. That is each Saturday it is 6 to 8, because we need to provide to NPTEL department uh, before starting the TA class. What is the specific time? So we have to form a Google form, and already we have submitted it. So if actually, what is the problem, sir? If I want to change, then again I have to mail, and again I don't know whether rest all have the they are okay with this time or not, or they have some problem, because it's okay, 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 sure, 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 sure. Okay, let me. I will just highlight your issue, and let's see what I can do. Okay, sure. So if you have any doubt, you should ask, because I have another 15-20 minutes. Otherwise, I will stop. You should know the. I just repeat that DMA is very important. Those are from a rubber background. DMA is very important. So you need to study, because DMA itself is a uh, syllabus. So I cannot cover within a 1 hour or 2 hour. But you need to study this DMA very deeply. Otherwise, you will not uh, get the importance, or you cannot probe the material behavior, physical behavior. So if you ask any question regarding DMA, so that will be also helpful for me. That's why I'm asking that DMA, why it is important. Otherwise, I'll stop. So I think you don't have any question. So I should, yeah, 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 yeah. Uh, could you please send me a mail so that I can reply you? You will get it from portal. So whatever the material or some reference if you need, so just mail me. I will respond. Welcome. Okay. So yes. Yeah. Good evening. Yes. Yeah. Yeah. Okay. Tan delta. Tan delta. Yes. Actually, see, from the DMA analysis, you are investigating or you are probing mechanical behavior of your material. So you are not probing the composition of your material. You are checking the performance under different mechanical environment. So what you need to know, what is the composition, or yes, okay, yes, okay. So what I will suggest, so based on filler loading, first of all, if you are increasing filler, your material will have a higher elastic component, and ultimately it will result with a higher Redox modulus and lower elongation at break. That is, if the material has higher filler component. Now it's not only filler, if it is cross-linked and if cross-link density is high, so again it will come to your elastic component. So there are different parameters, it's not single. If you are fixed all, if you are changing only one thing, from that you can say, okay, if I am fixing all the composition, only I am changing the amount of carbon black or whatever CNT or graphene. In that case, with increment of your CNT or graphene, you will get a higher elastic component and higher tensile strength, etc. Now you also need to know what is the distribution and dispersion, because in case of nanocomposite, the dispersion and distribution is very important. If it is not dispersed well, you will not get a homogeneous data. You will get different data from different part of your material. So for this you need to check the FSM image, whether the distribution is homogeneous or not. Otherwise you cannot yeah, otherwise yes, FSM, otherwise you cannot I mean always you cannot get that same result if the dispersion is a problem. So if you make if you made 6 sample, and if you are changing one component, then I will suggest, if it is a filler, you check just dispersion and distribution, then you will get some insight what is the problem happening there. Welcome. Yes, entanglement. From the DMA, you cannot say the entanglement. I mean, actually, what is cross-link density? Cross-link density is the number of cross-linking site per unit volume. So, say if you are using sulfur to cross-link your material, rubbery material, if you use higher pHr of sulfur, the cross-link density will ultimately higher. Now, higher the cross-link density, it means it is difficult to uh, mobile your, it is difficult for segmental mobility. Now, if cross-link density is higher, your elastic component is increasing. So from DMA, you will get that the this one, that is 1 minute, that storage modulus E prime with strain, it will remain as a higher if the elastic component is increasing, and loss modulus will be lower. That that means if the cross-linking density is high, so you will see that E prime will be higher than the E double prime with strain. But if cross-link density is low, maybe at a lower strain, your E double prime will dominating the E prime. If you plot the storage or loss modulus versus strain, if the cross-link density is higher, at higher strain, E prime will be E greater than the E double prime. If the cross-link density is low, E double prime will dominate E prime at a very small strain. So you need to check that at how much strain, that up to how much strain in the storage modulus is high or dominating than the loss modulus. That is the main thing. That at how much strain, up to how much strain, the E star is dominating in double prime. Understand? Y- Yeah. Yes. Yes. Sure. Okay. Okay. For vibrational application, I will suggest crosslink density should not be very high. If crosslink density is very high, your storage modulus will be high, so material brittleness will be higher. So it will not absorb energy. For example, we used to keep some table under a vibration or shock absorbance type of material. In that case, the modulus is not very much high. So if you increase the crosslink density, it will not absorb that vibrational energy. So it should not be very much high crosslink density. And actually, crosslink density we used to measure just by checking the change in volume. If you dip a crosslink material under a specific solvent, and if after certain time it will swell. Now, with increasing crosslink density, the swelling will be lower. In that way, we used to calculate the crosslink density by checking the weight of the material. Higher the crosslink density, the swelling will be lower. So I don't know whether there is any threshold or not for any application, and that I need to know actually. But for vibrational type application, your crosslink density should not be very high. That is for sure. Welcome. Okay. So anybody, or I should stop here? Okay. Thank you for your patience. And okay, I'll share my email ID. So okay, we'll meet next week. Till then, stay happy, Vandal. Thank you.